Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu, and in this video, we're going to talk about the electron configuration. This is a very important topic in Chapter 8, so please pay attention and really understand how it works. And this topic will for sure show up in the exam and also plays a very fundamental and important role in understanding many other electronic structures of the chemistry. So please pay attention. In our last video, we talked about different energy levels of orbitals. And now we'll take one step further to introduce the sequence of electron orbitals, the full sequence of electron orbitals. So for lower energy to higher energy level, the sequence of electron orbitals is 1s, 2s, 2p, 3s, 3p, 4s, 3d, and so on and so forth. It may not look very regular or have a order in when you write it out like this, but actually they are a very easy way for you to memorize or help you to establish the sequence of these electron orbitals. Just a reminder that electron orbitals are there whether or not it's occupied by electrons. So it's like the empty chair in the room. If there are more people in, more electrons get in, it sits in the chair. Otherwise, the chair is just empty, but they are there. So coming back to the topic about establishing the sequence of electron orbitals, we use the way called diagonal rule, the energy of the electron orbitals. The way it works is we write the electron orbitals in a matrix. So for each line, we write electron orbitals with the same principal quantum number. So for 1, we only have one s orbital. It occupies the first row. And in the second row, we have the 2s and 2p. Third row, we have 3s, 3p, 3d. For fourth row, we have 4s, 4p, 4d, 4f, and so on. And then in each column, we make sure the same type of orbital are in the same column. So the first column, we have 1s, 2s, 3s, 4s, 5s, 6s, 7s. The second column, we have 2p, 3p, 4p, 5p, 6p, 7p, so on and so forth. So now we've established this matrix, including all of the electron orbitals that possible you can find in an atom. Now the sequence is we start with the first orbital. We're writing a diagonal arrow from upper right to lower left. Okay. After cross out one electron orbital, we move to the second electron orbital, which are to the right of it. If there's no electron orbital to the right of it, we move to the next row. So in this case, we cancel out 1s. There's no orbital in the same row. So we move to the next row for the 2s. After we cross out 2s, we have in the same row, we have 2p. So 2p is the third one we start. So after 1s, 2s, we do the 2p, 3s, the diagonal arrow, and then 3p, 4s, the diagonal, and then the 3d, 4s, 4p, 5s, and then the 4d, 5p, 6s, and then 4f, 5d, 6p, 7s. So in this way, we wrote the diagonal from the upper right to the lower left to covering all electron orbitals in an atom. So that sequence of the electron orbitals that you see in this diagonal rules corresponding to the energy level from the lower level to the higher level of all electron orbitals. All right, so with this diagonal rule, we can easily come up with the sequence of electron orbitals. And if we have the sequence of electron orbitals, we can use the off-ball principle to fill in electrons in this electron orbitals. The off-ball it's a German word, means construction. It's basically using the building block of electrons to build the electron structure of an atom. So the Aufbau principle goes like the electrons fill low energy atomic orbitals before filling high energy ones. So into filling electrons in one s orbital first. After one s orbital is fully occupied by electrons, which are 2 electrons, right? And then we move on to the 2s. After 2s is fully occupied, we move on to the next level, 2p. So from the lower energy level to the high energy level. There is a recap of how many electrons are there in each orbital. So there are 1, 3, 5, 7 orbitals in the SPDF sublevels, respectively. And because of that, the maximum electrons in the SPDF orbitals are 2, 6, 10, 14, respectively. Each orbital can hold 2 electrons, spin up and spin down, right? All right, with this, we can write the full electron configuration. When we say electron configuration, it's like how the electrons sitting in each of these orbitals. And when we do that, for a given atom, if we are asked, we need to write the full electron configuration, we need to fill in electrons based on the Aufbau principle. Let's take a look at the example together. Write the electron configuration of phosphorus. How to do that? You can take out scratch sheet and try it out by yourself. Okay, so first we need to write out the sequence of sublevel orbitals using the diagonal rule. So here I just quickly show up the diagonal rule here. So the first few ones, then 1s, 2s, 2p, 3s, 3p, 4s. I just write a few. If it's not enough, I can add more later on. Okay, so second step is to calculate how many electrons the atom has in total. For phosphorus, we can refer, because it's an atom, we can refer to the number of protons to calculate the number of electrons. And then the number of protons can be found as the atomic number in the periodic table. So for phosphorus, it's the number 15 in the periodic table. That means there are 15 electrons here. The final step is the construction step, right? We can fill in electrons based on the sequence of orbitals until all electrons are used up. We need to indicate the number of electrons in each orbital as a superscript on the right side of that specific orbital. Okay, so in this case, we have 15 electrons in total. For s orbital, at maximum, it can hold 2 electrons. Then we have 13, right? 13. For 2s, it can also hold 2 electrons at most. So, of course, we can afford that. 13 minus 2 equals to 11. For p orbitals, there are 3 orbitals here, so 3 times 3 at most, it can hold 6 electrons. We can still afford that. So left over is 5. 3s orbital is an s orbital again, so it can take 2 electrons, and we only have 3 electrons. For p orbital, 3p orbital, it can maximum take 6 electrons, but now we have 3, so yeah, of course it can hold 3 electrons. And that p orbital is not completely filled, but since we run out of electrons, and that's it. Okay, and based on this, we can write out the full electron configuration of phosphorus. 1s subscript 2, 2s subscript 2, 2p subscript 6, 3s subscript 2, and 3p subscript 3. Okay. Sometimes when we move on to the 4s and 3d, then the sequence of the sublevel orbitals will be, 3p, 4s, and 3d. I'll just write it here. Sometimes we have 3p, 6, say 4s2, 3D, I'll just make it up, 1. In this case, the final step, we can rearrange the sequence of this electron orbitals as 3p6, 3d1 orbitals with the same principal number we can put together, then the 4s2. Okay, so either way is fine to write. Okay, this is a step 4, but this is optional. Okay. All right, so just to recap, the electron configuration of phosphorus is 1s2, 2s2, 2p6, 3s2, and 3p3. For all of electron configurations of any atoms, they follow the same pattern, that the 1s, 2s, 2p, those are the name of a sublevel orbital following a principal energy level. Okay, basically it indicates which electron orbitals are there. And for the top subscript, these are the number of electrons in each group of sublevel orbitals before it. Okay, based on the electrons that fill in the highest level, in this case, the 3p level, right? So based on what are the highest energy orbital that have electrons filled in, we can divide all elements in periodic table into different sublevel blocks. The 1a and 2a column are 1s or s block. 3a to 8a main group columns are p block. So the transition metal 3b to 2b, which is column 3 to column 12, is d block. And usually in periodic table, we have the extra two rows, right? Those 2 rows are f block. And with this blocks, or with one step further about these electron configurations, we can actually divide electrons into valence electrons and core electrons. Valence electrons means the outmost electrons, or electrons in orbitals with the highest principal energy level, principal quantum number. Core electrons are electrons in the inner energy level, or other electrons except for valence electrons. Take the phosphorus as an example. We have its electron configuration written as this: 1s2, 2s2, 2p6, 3s2, 3p3, right? So for the valence electrons are the electrons in the most outside position. In other words, electrons with the highest principal quantum number 3. So and other than 3, the inner shells are all core electrons. So in this case, principal quantum number 1 and 2 corresponding to core electrons. In this case, 2 plus 2 plus 6, that equals to 10 core electrons. And the valence electrons are the electrons corresponding to the highest principal quantum number 3, which is 2 plus 3, that equals to 5 valence electrons. Okay, now if we can define which one's a core electron, which one's valence electrons, we can write an easier way of the electron configuration. That's called condensed electron configuration. From the name, you will know it's shorter than the 4 electron configuration. So here, table 3 shows main group element from sodium to argon with this 4 electron configuration. Okay. The third column, partial orbital diagram, we can ignore it for now. Okay. For the 4 electron configuration, if you pay close attention to it, they share the same electron configuration in the core level, 1s, 2s, and 2p, right? So if they are all the same, is there any way we can replace it to write it in a simpler way? And yes, there is. So if you pay closer attention, the noble gas on the 1 row before it, so now the sodium and argon on the 3rd period, so the row before it is the 2nd period, and then the noble gas in the 2nd period is neon. right? So electron configuration for neon is 1s2, 2s2, 2p6. That is exactly the core electrons, the configuration of core electrons of all the sodium to argon atom. So in order to make the full electron configuration easier to read and make it more concise, we can replace the core electron configuration with the noble gas in the previous row. So now the sodium to argon electron configuration can be written as the atomic symbol of neon and E in the bracket. So bracket and E bracket for sodium is 3s1. For say chlorine is bracket and E bracket 3s2, 3p5. When we write the condensed electron configuration, after we put the noble gas in brackets, we always start with the s orbitals in the same period of this atom. So just take a few examples here. If we're looking at and say potassium, for example. Potassium, after we write the noble gas in the previous row, which is argon in bracket, we always start with the ns orbitals of potassium. So potassium is in the fourth period, so we start with the 4s orbital. Okay, potassium has a number of 19, argon has a number of 18. We only have one more electrons, so we're filling that with 4s1. So this is the condensed electron configuration of potassium. Potassium is bracket argon, bracket 4s1. Let's take a look at, say, bromine, which is in the same period. For bromine, after we put argon, the noble gas in the previous row, argon has a number of 18, bromine has 35. 35 minus 18, we have 17 more electrons. Okay, we still start with 4s. Okay, for 4s, we can have 2, but also if we see after 4s using diagonal rule, we have 3d. Okay, 3d, d orbital can take up to 10 electrons. So yeah, we can put 10 electrons here, and then the 4p orbital. So after 4s, 3d used up 12 electrons, we have 5 electrons left over in the 4p. So in this case, the bromine, the condensed electron configuration of bromine is argon 4s2, 3d10, 4p5. So you just need to focus on starting with the 4s and move on using the same off-ball principle and the same diagonal rules. Okay, just make things easier, starting with the ns of this atom. All right. There are a few actually exceptions of off-ball principle, so we're going to talk about that. I listed the diagonal matrix here and also a periodic table. A few atoms in the periodic table in the transition period or D block has exceptions of off-ball principle. Those are in the 6B column, chromium, molybdenum, and those are in the 11 or 1B column, copper, silver, gold. So I'll just list out their condensed electron configuration here. For chromium, we have argon, then 3d5, 4s1. So the exception is we should originally fill in 2 electrons in 4s and then 3d. So it should be, the 4s should not have 1 electron, it should have 2, but now it only has 1. And then for molybdenum, after krypton, we have 4d5 and 5s1. For copper, we have 3d10, 4s1. Silver, we have 4d10, 5s1. And for gold, we have 4f14, 5d10, 6s1. So if you look at these exceptions, there is actually a trend. That is, when d orbitals are half filled or completely filled, we need to fill in d orbitals first, then the s orbital in the next level. So for chromium, we need to fill in half fill the d orbitals, 3d5, and then the s orbital 1. Okay, the 1 electrons in the s orbital. And for copper, silver, and gold, we need to fill in d orbitals as 10 electrons, and then the 1 electron in the s orbital. So pay attention to these exceptions. Now you know everything about electron configuration that is required for general chemistry 1. So how to write an electron configuration of an atom. So then how about electron configuration of a cation? So cation are atoms that lose electrons, right? So this is actually slightly different of how to write electron configuration than an atom. So step 1, we need to write an electron configuration of the corresponding atom. And then step 2, get the number of lost electrons from the carrier charge. So if it's +1, there's lost 1 electrons. If it's +2, it loses 2 electrons. Okay. Step 3, delete the number of lost electrons from the atomic electron configuration, starting from the outmost layers, the layers with the highest principal quantum number and the highest L value. Okay, let's take a look at example. What is the electron configuration of copper 1+? You may take out the spreadsheet and try to figure it out yourself. So we need to write the atomic electron configuration of copper first. Copper has argon, 3d10, 4s1. No, it's one of the exceptions. So when we take 1 electron away from the copper to make the copper 1+, we only need to take 1 electron away. We take from the outmost electrons. So it's the 4s. Okay, 4s1 electron. So the copper plus will have argon 3d10. So another example, what is the electron configuration of lead 2+? We need to write the atomic electron configuration of lead first. So lead is xenon 4f14, 5d10, 6s2, 6p2. Okay, when we start to lose, and then determine how many electrons it loses. It loses 2 electrons to make it 2+. So which 2 electrons to lose is the outmost layers. So first is the quantum number, the highest quantum number 6, and then the highest L number p. So we lose 6 p orbitals first, and then just get rid of these 2 electrons. The lead 2+ has an electron configuration of xenon 4f14, 5d10, 6s2. Okay, so then you may wonder, how about anions? Anion gain electrons, how to do that? If you need to write electron configuration of anion, it's the same rule as writing electron configuration of atom. You need to write the sequence of energy levels and then calculate how many total electrons you have. So in this case, you need to add the actual carrier charge of electrons to the atom, right, to calculate the new total number of electrons, and then use the alpha rule to establish the electron configuration. All right, this is the end of this video, and I'll see you next time.